This is part 2 of lecture 2.1 of Math 108, Direct Proof. In this video, we give more variations of direct proof of conditional sentences. You are expected to have watched part 1 before proceeding with this video. Consider the case where the claim is a conditional sentence whose consequent is a conjunction. Recall from a previous exercise that the propositional form P implies both Q1 and Q2 is equivalent to the conjunction P implies Q1 and P implies Q2. Hence, to prove that P implies both Q1 and Q2, we need to prove that P implies Q1 and P implies Q2. That is, using the same hypothesis P, we first deduce Q1 and then we deduce Q2. For example, consider the claim if A equals C and B equals D, then A plus B equals C plus D, and A times B equals C times D. Let P1 be the sentence A equals C, P2 be the sentence B equals D, Q1 be the sentence A plus B equals C plus D, and Q2 be the sentence A times B equals C times D. Then the claim is a conditional sentence whose antecedent is the conjunction P1 and P2 and whose consequent is the conjunction Q1 and Q2. To prove the claim, we need to prove that A equals C and B equals D implies A plus B equals C plus D, and A equals C and B equals D implies A times B equals C times D. A direct proof of the claim begins by assuming that A equals C and B equals D. In the first part, we shall deduce that A plus B equals C plus D, and in the second part, we shall deduce that A times B equals C times D. Assume that A equals C and B equals D. Applying the addition property of equality to the statement A equals C gives us A plus B equals C plus B, and applying it to B equals D together with the commutative property of addition gives us C plus B equals C plus D. Hence, by the transitive property of equality, A plus B equals C plus D. This completes the first part of the proof. For the second part of the proof, we do not need to state again the hypothesis that A equals C and B equals D. This hypothesis is understood to still hold. This time, applying the multiplication property of equality to the statement A equals C gives us A times B equals C times B, and applying it to B equals D together with the commutative property of multiplication gives us C times B equals C times D. Hence, by the transitive property of equality, A times B equals C times D. This completes the second part of the proof and completes the proof of the claim. Consider the case where the claim is a conditional sentence whose consequent is a disjunction. Recall that the propositional form P implies either Q1 or Q2 is equivalent to the conditional sentence if both P and Q not Q1, then Q2. Hence, to prove that P implies either Q1 or Q2, we need to prove that if both P and not Q1, then Q2. For a direct proof of this statement, we assume that the conditions P and not Q1 both hold and deduce Q2. Note that in this proof, the roles of Q1 and Q2 are interchangeable. The choice of which condition is used for Q1 and which condition is used for Q2 depends on how easy or difficult it is to deduce Q2 from P and the negation of Q1. For example, consider the claim if A times B equals 0, then either A equals 0 or B equals 0. Let P be the sentence A times B equals 0, Q1 be the sentence A equals 0 and Q2 be the sentence B equals 0. Then the claim is a conditional sentence whose antecedent is P and whose consequent is the disjunction of Q1 and Q2. To prove the claim, we need to prove that AB equals 0 and A non-zero implies that B equals 0. Alternatively, we can prove that AB equals 0 and B non-zero implies that A equals 0. A direct proof begins by assuming that AB equals 0 and A is not equal to 0. We shall deduce that B equals 0. Assume that AB equals 0 and A is non-zero. Since A is non-zero, it follows from the existence of multiplicative inverses that A has a multiplicative inverse 1 over A. From the hypothesis that AB equals 0 and from the multiplication property of equality, we get that 1 over A times AB is equal to 1 over A times 0. By the associative property of multiplication, 1 over A times AB is equal to 1 over A times B. By the transitive property of equality, we then get that 1 over A times B is equal to 1 over A times 0. Since 1 over A is the multiplicative inverse of A, 1 over A times A is equal to 1. Hence, by the multiplication property of equality, 1 over A times B is equal to 1 times B. Thus, by the transitive property of equality, 1 times B is equal to 1 over A times 0. Since 1 is the multiplicative identity, 1 times B equals B. Thus, by the transitive property of equality, B equals 1 over A times 0. Recall that by example 3, any real number times 0 is equal to 0. So 1 over A times 0 equals 0. Therefore, by the transitive property of equality, B is equal to 0. This proves the claim. We can apply the previous proof methods to give a two-part proof of a biconditional sentence. Recall that the proposition P if and only if Q is equivalent to the conjunction of the conditionals P implies Q and Q implies P. To prove P if and only if Q, we need to prove the conjunction P implies Q and Q implies P. Hence, the proof consists of two parts. One part to show that P implies Q, and another part to show that Q implies P. For example, consider the claim AC equals BC if and only if either A equals B or C equals 0. Let P be the sentence AC equals BC, Q1 be the sentence A equals B, and Q2 be the sentence C equals 0. Then the claim is a biconditional of the form P if and only if either Q1 or Q2. A two-part proof of this statement consists of the proof of if AC equals BC, then either A equals B or C equals 0, and the proof of if either A equals B or C equals 0, then AC equals BC. The statement if AC equals BC, then either A equals B or C equals 0 is a conditional sentence whose consequent is a disjunction. Thus, a possible direct proof begins by assuming that AC equals BC and C is non-zero, and deduces the statement A equals B. The statement if either A equals B or C equals 0, then AC equals BC is a conditional sentence whose antecedent is a disjunction. Thus, a direct proof consists of two cases. In the first case, we assume that A equals B and deduce AC equals BC. And in the second case, we assume that C equals 0 and deduce AC equals BC. Assume first that AC equals BC and C is non-zero. Since C is non-zero, it follows immediately from the cancellation law for multiplication, which we proved in example 2, that A equals B. This completes the proof of this direction. We now prove the converse. For case 1, assume that A equals B. Then by the multiplication property of equality, AC equals BC. This completes the proof of case 1. For case 2, assume that C equals 0. Then by the multiplication property of equality, AC equals A times 0 and BC equals B times 0. By example 3, A times 0 equals 0 and B times 0 equals 0. So by the transitive property of equality, A times C equals 0 and B times C equals 0. Again, by the transitive property of equality, we get AC equals BC. This completes the proof of the claim. Another way of proving a biconditional sentence is by a one-part proof. Recall that for propositions P, Q, and R, if P is equivalent to R and R is equivalent to Q, then P is equivalent to R. Thus, a one-part proof of P if and only if Q begins by finding a statement R1 that is equivalent to the statement P. We then find a statement R2 that is equivalent to the statement R1. We continue this process until we find a statement Rn that is equivalent to Rn minus 1 and equivalent to Q. By the transitive property of equivalence, it then follows that P is equivalent to Q. An example of this type of proof will be given later. Consider a claim of the form P if and only if Q, if and only if R. This can also be stated as the following are equivalent: condition P, condition Q, and condition R. P if and only if Q, if and only if R means that P, Q, and R are pairwise equivalent. That is, this is equivalent to the conjunction of the statements P if and only if Q, Q if and only if R, and R if and only if P. It can be shown that this is equivalent to the conjunction of the conditional sentences P implies Q, Q implies R, and R implies P. The proof of this equivalence is left as an exercise. Hence, to prove that P, Q, and R are pairwise equivalent, we only need to show that P implies Q, Q implies R, and R implies P. The proof will then have 3 parts showing each of these conditional sentences. An example of this type of proof will be given later. You have come to the end of part 2 of lecture 2.1. You may now proceed to lecture 2.2. Thank you for your attention.